So first of all, I'd like to warmly thank the organizer for inviting me to this meeting. It's really a great honor to be here. Thank you very much. So what this little picture illustrates is that I'm going to talk about renormalization group, so more precisely functional renormalization group, and I will try to show you what can be learned from it in turbulence and related models. So my talk will be divided in two parts. So the main part will be about Navier-Stokes equations, and I will try to explain, to motivate why renormalization group should be useful at all to study turbulence. And in fact, after I will start by stating our main result, the main result that we obtained so far, and which is about the time dependence of correlation functions in turbulence. And then I will, in fact, compare this prediction with results from direct numerical simulation to make it a bit more concrete, what it means. And the last bit will be the technical part, where I will try to explain you how we obtain these results. But I've kept it really schematic because I guess most of you are not familiar with RG. So it's really just to give you a flavor, the main idea of what does the derivation rely on. And then second part will be about stochastic burgers or Carter-Paris-Long equations. And it will be about a new scaling regime that, in fact, we were able to explain. OK, so let me acknowledge all my collaborators on this work, and in particular the students here, who did really a tremendous work on this, and they made great contributions. OK. So let me start with very simple things. So what we are after is a statistical theory of turbulence. And following Kolmogorov pioneering ideas, if you consider that in the cascade, the only relevant quantities are the energy flux and the AD size, then what you find is the structure functions, so which are the moment of velocity increments, behaves as power law with an exponent which is linear. And apart from this result for S3, which is exact, the rest come from dimensional analysis. But of course, you know that from numerical simulation and experiments, this is not what is observed. So the structure functions do behave as power laws, but with an exponent which deviates from this linear prediction. And this is what is represented here. So this is the exponent as a function of the order. So this is called Kolmogorov. And this is observation from experiments and numerics. And this is referred to as multifractality, intermittency, as you well know. And those are also called anomalous exponents because they do not conform to dimensional analysis. This concerns equal time quantity structure function. But now, if you look at temporal dependence, so again, following Kolmogorov, you can construct a typical decorrelation timescale, which goes like k to the minus 2/3. But in experiments on numerical simulations, this is not what is observed. What is observed is rather a k-1 decay, as is shown here, in particular large k, where you deviate from this prediction and you reach a k-1. So this is usually interpreted as a consequence of the random sweeping effects, which means the random advection of small-scale velocity by the large eddies of the flow. And again, it's a challenge to explain that from first principle, that is directly from Navier-Stokes equation. And this is what we are going to try to do. OK. And so for that, the approach that we are interested in is calculation from first principle. And in fact, all what I've just described is really reminiscent to what happened for critical phenomena. If you think as, for instance, an Ising magnet at the critical temperature, where how would you describe this critical state? It's scale invariant, self-similarity. It has universality, same behavior in many systems. And it has anomalous critical exponents. And this critical behavior arises from the fact that you have fluctuations emerging at all scales, that your system becomes strongly correlated. And in fact, Wilson's renormalization group was precisely invented to deal with that. That is to account for these fluctuations at all scales. And it was very successful for critical phenomena. Okay? And the idea is to do a progressive, so since you have fluctuations at all scales, instead of trying to integrate them all at once, you're going to try to integrate them progressively in wave number, starting by large wave number. And doing so, what you are doing is building an effective theory, the theory that takes into account all fluctuations. And in fact, the idea that using this similarity, RGs should be useful for turbulence as well, because what I've described is the same thing, power law, universality, anomalous exponents. So the idea dates back to the mid-70s. But there was one difficulty. And in this framework, scale invariance, so a scaling regime, corresponds to a fixed point of the renormalization group equation. So since we are talking about integrating averages over fluctuations, so our starting point is the equation Laurent presented. So it's a Navier-Stokes equation in the presence of the stochastic forcing. And this forcing is chosen with a Gaussian distribution. And it has a covariance with something which is smooth, and it's picked at the integral scale to have a large-scale forcing. And this is just a way to generate an ensemble of trajectories, right? Because you have a trajectory for each realization of the forcing. And then you will be able to compute statistical properties by averaging on this ensemble of trajectory. And in fact, it's convenient to represent all these trajectories in a path integral. Okay, so this object just sums over all possible trajectories generated by this evolution. And in fact, it's well known how to cast this stochastic PD into a path integral. And what you obtain is this, and it has, in fact, a very simple structure. The deterministic part of the equation just comes with a linear term in this field with a bar, which is called response field. And same for the incompressibility constraint. So it comes linear in the response pressure. And those are really just like Lagrange multiplier to enforce the equation of motion. And then this allows you to perform the Gaussian integral. So you end up with a term which is quadratic from your Gaussian integral with the profile of the noise which comes here. OK. So this is our starting point. Yes?
Encode the initial data in the path integral.
You don't. We are interested only, you can, but they come as boundary term if you insist on that. But here we are really interested in stationary properties. Okay? And instead of averaging over different initial conditions, we average over different realization of the forcing. And in fact, to describe the universal properties, this is equivalent.
So are you taking average over all the initial data in the path integral?
Yeah, in fact, it's not a problem if you don't have what you require, if you don't have a unicity of solution, as long as they are on a set of zero measure. So it can have several, you can still write it if you have non-unique solutions. We can discuss that after if you want. OK. And in fact, the difficulty came that the original Wilson's renormalization group was really intimately related to what is called the epsilon expansion. And in fact, the initial review by Wilson and Kogut was called the RG and the epsilon expansion. Epsilon meaning a distance to a critical dimension or a size of a coupling of the nonlinearity. Okay? And in fact, people knew only how to exploit this framework within an epsilon expansion. But the problem is for Navier-Stokes, you don't have such an epsilon. Because the nonlinearity here, the coefficient is not epsilon, it's not small, else you just kill the turbulence. And you don't have something like an upper critical dimension above which fluctuations would become negligible. And so the way to circumvent that was to introduce a small parameter via the forcing covariance. So instead of having it concentrated at the integral scale, you put it as a power law. But if you do that, you obtain a spectrum which is epsilon dependent And K41 scaling is recovered for a very large value of epsilon, so we can question the validity of this expansion. And universality is really difficult to explain in this framework. So in fact, I will use another implementation of Wilson's RG, which is called functional RG, which I will explain later, and which completely bypasses this difficulty. Because you can do perturbation theory if you want to, but there are other ways to exploit this equation, which I will explain after. Okay? So with this, let me state the result that you can obtain in this framework. And I think the first result was to show that for a large-scale forcing, so this is in momentum space, so a forcing which is concentrated around the large scale, the integral scale, indeed, turbulence corresponds to a fixed point. And for instance, you can look at the viscosity. So you start from constant viscosity, and the effective viscosity that you build become momentum dependent. And from that, in fact, you can compute the statistical properties of turbulence that you obtain. And what you find is first they are universal. So you can vary the shape of the forcing. As long as it's picked at the integral scale, it does not depend on it. And this is the result. For instance, if you compute the second-order structure function, you find that it behaves as a power law with essentially Kolmogorov exponents. You can compute the constant, and it's very close to what is typically found in experiments. And this is S3, and for S3, you recover at small r the exact result by Kolmogorov. Okay? So this is the first nice thing that you can have that turbulence is indeed a fixed point of the RG for a large-scale forcing. But the main result that I want to discuss in more detail is the following. So the object we are looking at is correlation functions. So we are looking at how n velocities, depending on n space-time points, are correlated. Okay? So if you know all of these objects, you have your statistical theory of turbulence, right? Because you know all the moments, the correlation function. So this is the object we would like to compute. And we've been able to show one thing, that if you take a particular limit, which is, so you have an homogeneous system, so you can go to Fourier space. And if you take the limit where all the wave number are large, okay? All of them are large, and also their partial sum are large, then this object has the following asymptotic behavior. So don't worry about the expression. It looks complicated, but I'm going to illustrate it at length after that. What is important is that you see that the term is red. So this term is calculated exactly, so it's exact. It's of order k squared, right? And the correction, the next correction is of order k max, okay? And what I'm going to explain, if you look at this formula for the two-point function, then you can recover, in particular, that at small times, you have this scaling for the decorrelation time, so I will show that. But here, then you have the general expression for any correlation function. And an important feature that I will explain is that, in fact, you see that the coefficient in front of this, in fact, does not depend on n. So it's the same for any order, these coefficients. And in fact, the surprise was that beside this, which you can, so this small time regime, which you can relate to sweeping, there is another time. So there is a crossover at large time where the correlation will dramatically slow down, as I will show in a minute. So let me comment on that. And for this, I will compare with results from direct numerical simulation to show what there is in this formula. OK. So the simplest object to calculate is a two-point function. So this is a velocity. And this is what the formula looks like at small time. And you see that this formula predicts that it should be a Gaussian in KT. OK? And OK, we did numerical simulations. And the difficulty is you really want the time dependence. So it means that you have to keep in memory your velocity to correlate many time frames and do averages over that. So it takes quite long. And this is the result. So the dots are the numerical point, and the line are Gaussian fits. So you see that they indeed very well describe the data. And as k increases, it decorrelates faster, as you would expect from that. And another way to illustrate this is that if you divide by this, and if you plot instead of as a function of t as a function of the scaling variable kt, everything should collapse onto a single Gaussian. And you see if you go from t to kt, indeed everything collapses, which is a confirmation of this formula. Okay? This is for the two-point function. Oh, okay, sorry, another comment regarding the time scale. You can extract from this formula the typical decorrelation time, right? And you can also extract it from the numerics just from your Gaussian fit. And so the numerics is shown here. And you see that indeed it exhibits this k-1, which is precisely what you obtain from the formula above. And this is really similar to the first picture I've shown in the introduction, except that we went at higher k. And it's also similar to another result from Laurent and co-collaborator, because this scaling implies that if you now look at the spectrum in frequency, then since the ratio between frequency and k is 1, you should find the same spectrum, omega to the minus 5/3, so the same exponent as in space, and not omega to the minus 2, which you would obtain using the Kolmogorov time scale. Okay, so this is just a confirmation of this, which was found before. And okay, you can do in principle, you have a formula for any n, so in numerics we could do only n equals 3, and a specific configuration of n equals 3 because it becomes quite complicated. And what we looked at is an advection velocity correlation. So you take the advection term at a time, and you correlate it with the velocity at a later time. And if you write what it is, in fact, it is a combination of the three-point function, the general three-point function. And if you look at what they are at large k, because the prediction of RG is only valid at large k, it tells you that you should, again, obtain a Gaussian in kt for this specific observable. And this is what we observe also in the numerics, so the dots are the numerical points. As a function of t, they are all fitted by Gaussians, and everything collapses when plotted as a function of tk. Okay, so which is a verification for the three-point function. And also, I haven't shown it here, but we checked that this coefficient that we measure from the three-point function is indeed the same as from the two-point function. Okay, so this is for small time, but what about large time? So I've told you that at large time, we expect a crossover, and this crossover is towards something which is much smaller, because you go from something that decay like t squared to something that decay exponentially. Okay? So in fact, in Navier-Stokes simulation, this is really hard to observe because the initial Gaussian decay is very fast, and you are still you are very rapidly in numerical noise. So sometimes you see it, but it's very difficult to have it converge average values. But interestingly, in fact, there is this experiment which was performed in a turbulent air jet, and where, in fact, they measure the covariance, and they fitted it with a Gaussian at small time and an exponential in the tails. And this is exactly the kind of crossover we are after. But however, here, what they looked at were rather correlation of the modulus. So it would be cheating to say that it's the same quantity, but this is the kind of crossover we are after. And in fact, we were able to observe it in the case of passive scalar turbulence. So passive scalar means a scalar, which could be temperature or some particle, like a cloud of smoke or salinity or whatever, and particle transported by a turbulent flow. So this kind of particles satisfy a diffusion advection equation. Okay, so we studied that when V is a Navier-Stokes field, but it's also interesting to study when V is a synthetic random field, so which is really the spirit of Kraichnan model. So in Kraichnan model, the velocity is chosen Gaussian, which prescribe covariance, and its mass, it depends in a parameter epsilon, which is the older dimension, as Laurent was presenting, of the velocity field. So it goes from very rough when epsilon tends to 0 to very smooth when epsilon tends to 2. And in the original Kraichnan model, it's just delta correlated in time. here we slightly generalized it by considering some finite time correlation, okay? Finite with a typical time scale tau. So Kraichnan limit is tau to 0. And what is interesting is, so first we did the calculation with functional RG, and in fact you find a very similar behavior in time. So in the limit where k, the wave number, is large, what you find is a typical crossover should occur from a Gaussian at small time to an exponential at large time. But in this case, this tau can be controlled by your synthetic velocity field. So you can tune it independently of the internal time scale of your scalar, okay? And so we computed that, and we could really observe this crossover. So here again, the dots are the numerical points. So you see at small time, they can be fitted by a Gaussian, but after, at large time, they deviate from this Gaussian, and they slow down to something which is in fact exponential. So you can visualize it if you take the log of this quantity, you take the time derivative, and you normalize everything by k squared. Everything should collapse onto a constant, a negative slope at small time to a negative constant at large time. And this is what we observe in these numerics. And in fact, you have, if tau goes to 0, you have a simpler limit. You see the Kraichnan limit corresponds to sending this tau to 0, so you just kill the initial Gaussian regime. So you end up with a pure exponential decay. And so this is what you obtain. And in this case, in fact, this model can be solved by many other means. So it's a similar result that were obtained before. And not only you have the decay, but in this case, you can compute explicitly the amplitude in terms of the property of your carrier of fluid, okay? And within many simulations, varying the property of the velocity field, so you can vary the older exponent, its amplitude, the diffusivity of the scalar. So we did many sets of simulation, and each time we extracted the slope. So this is the decay in k squared t. We extracted the slope, and we compared it with the direct analytical estimation of that. And in fact, for all the sets of our simulation, it really matches what we found in the simulation. So here it's nice because it's a non-universal amplitude that is computed. OK. So if you allow me, I will just, for 10 minutes, explain how we derive this result. And if you don't want, you can just take a nap and catch back 10 minutes later. Yes?
I have a question about your results on the correlations. I don't know if you want.
I can hear you. But...
Oh, great. So it looks like for t small, the endpoint function becomes a product of two-point functions. Can one read that in the sense? Is it not correct to read that in the sense that for small times you have propagation of chaos and a renormalization group asymptotically free theory, while for large t you have loss of propagation of chaos and you have an interacting renormalization fixed point?
Thank you for the remark. I have to think about it. I cannot answer right now. I have to think about it. I don't know. I don't know. The answer is I don't know. I'm not sure about the decorrelation because, OK, maybe we can discuss later. Yes?
What about the functional RG is necessary for doing this calculation? What are the things that you cannot do with Wilson-Fisher renormalization? Or is it just a more efficient way of doing the calculation?
This, I have no idea how to do it within an epsilon expansion because it's really a completely different regime that I'm looking at. I'm looking at a large K regime, and I really need the interaction to be what they are. I don't want them to send them to 0. Because it will.
Thank you.
But maybe it will become clearer in some details. So let me go through that, but not too long. So
that's the most interesting part.
okay, but maybe not for everyone, I don't know. Well, for the rest, you can sleep. So the functional renormalization group is really based on this Wilson idea that I explained. So the idea is to do a progressive average over fluctuations. And in fact, I think the major advantage of this formulation is that in the original Wilson RG, the effective theory, what you are building is a flow of effective Hamiltonian or effective action. But this is quite an abstract object. I mean, this is not something that you can measure. Plus, if you want to compute some statistical average, you still need to do the functional integral to compute this average. And in fact, the whole idea of this formalism is to directly look at the flow of something which is measurable. And in fact, that includes all your fluctuation. And this object, which is called gamma, is just your thermodynamic potential if you were at equilibrium. Okay? So this is a quantity that already contains all your average, all the average physics that includes all the fluctuation. This is measurable, and this is a precursor of your true thermodynamic potential once you have integrated all the fluctuation. Okay, and to do this progressive average, in fact, what you do is you introduce this kind of function, which is a very smooth function, which is called a regulator. And what it does is that it gives a weight, a scale-dependent weight in your functional integral. And you see that at small k, you just give a large mass to this mode, and you will just suppress their contribution from the functional integral so that you don't integrate over the small momentum mode that you don't want, okay? So it's just a way to split, as in the original Wilson's idea, the fluctuation between the modes, between the one you want to integrate and the other one. And in fact, the object we are looking at is defined as the Legendre transform of log z, which is a free energy. So this would be Helmholtz free energy, and you just go to Gibbs free energy, okay? And this gamma would be really Gibbs free energy. And in fact, the evolution of this object as you integrate the scale is given by an exact equation, which is not difficult to derive, which tells you how this object evolves as you integrate your fluctuations. And essentially, pictorially, what it does is that it integrates from the microscopic scale, where you have just your action, to when you have integrated all your fluctuation, it just gives you your thermodynamic potential, okay? And in fact, this equation is just a PDE, a deterministic PDE. So for mathematicians, which I know don't like at all path integral, at this stage, you don't have any more path integral, okay? This is just a PDE. So you can just take that this is our starting point, this exact equation that gives you the evolution of your theory as you integrate the scale. Okay, and in fact, so remember that the object we are after are the endpoint correlation function. And this correlation can be obtained from this equation just by taking functional derivative with respect to this. You see the log z, in probability, it would be your characteristic function, right? So if you take derivative, you can generate all the moments. So this is the same thing. By taking derivative with respect to this, which you have coupled linearly to the field, you will generate all the correlation function, okay? And so once you have the exact equation for your generating function, you just take n derivative, and you end up with the flow equation for any correlation function. So it's not important the precise form. The only message here is that this equation is exact, but it's not closed. Because you see, you start from an equation where you already have derivatives here, okay? So let's say if you take n derivative to have the flow of this object, you will end up with objects which involve n plus 2 or n plus 1. So in fact, you have an infinite hierarchy of equations, but as usual with nonlinear system. I mean, if you write the moments in Navier-Stokes, you have an infinite hierarchy as well. And what I'm going to explain in 5 minutes now is, in fact, if you take a specific limit, which is the limit where all these external wave numbers are large, then you can close this equation exactly without other approximation than this large k limit, okay? Okay, so, and the main ingredient, in fact, is symmetries, or more precisely, what I will call extended symmetry. So I will call an extended symmetry a transformation of the fields and coordinates, which does not leave the action strictly invariant, what you would expect for a symmetry, but which can lead to a variation, but which is at most linear in the field. Okay? And in fact, it turned out that if you have such, so an extended symmetry, so something that leads to only a linear variation, you can derive identities which are called functional, which are called word identities, and they are extremely constraining because they tell you that the variation of gamma under this symmetry has to be the same as the variation of your action. And in fact, it really fixes a whole dependence of this object. Okay? And again, this object generates a whole set of correlation functions. So they are called vertices. And so this is their definition. You just take functional derivative with respect to field and response fields. But it's not really important. What is important is since gamma and W are just Legendre transforms of each other, this set of correlation is strictly equivalent to the set of correlation functions we are looking at. Okay? So they contain exactly the same information, and you can reconstruct one set if you know the other. Okay, so let me tell you what are these symmetries now. The first one, well, we start from something which is very, very well known, Galilean invariance. So it means you just add a constant velocity to all the velocity of your fields. Okay? But you can allow, in fact, this velocity, instead of being a constant, to be time-dependent, okay, but infinitesimal. And in fact, if you look at the variation of the action under that, the variation is linear of the field, in the field. And you obtain from that an infinite set of exact word identity. And what they tell you, so don't bother about the precise form. What is important is m plus 1 here and m. Okay? So what it does is lower the order of your correlation function. And when does it do that? As soon as you have a zero momentum carried by a velocity. So if you have a zero, then you lower by 1 the order. And this is exact, and this operator is essentially a finite difference operator. It's not important in its precise form. And this, in fact, was kind of well known in the literature of Navier-Stokes in the 90s. But in fact, there is another one which was not well known, and which is essentially a shift in the response field sector. And if you do that again, you obtain wide identities. And here it's an extreme reduction because, in fact, they just vanish. And they vanish when you have a q equals 0, but this time carried by a response velocity. So it means, in fact, if you have a q equals 0 on any of the leg, you can lower the order. And how can you exploit that? Well, very simply. So don't worry, it will be very schematic. Very simply by taking this limit of large k. And the reason why it will lead, you can control this limit is because of this little red cross. These little red cross are just a scale derivative of this very smooth function that separates your mod. Okay? And the property of this function is that it's exponentially suppressed at large k. So first, if you consider this limit where all the k and also all their partial sums are large, you can just forget about that because what goes through there is precisely this combination, and they're exponentially suppressed. And here, in the other thing, in fact, the loop means that you have an integral over q. But this integral, by construction, is cut to your RG scale here. So it means that q is bounded from above by k. So now if you consider an external k which is large, then q is negligible with respect to this external momentum. Okay? And it means, in fact, that you can expand the vertices in powers of q over p, because q over p tends to 0 in the limit of large p. And if you do that, it just amounts to setting q equals 0 here on 2 legs. So you add at most n plus 2, you lower by 1, and then you use extended symmetries, and this equation is closed. Okay? And so you have this kernel here. So you can see that this operator that we have before appears, but it's not important. It's of order k square. What you neglect is of order k. And also an interesting property is that you see it could depend in principle on the whole hierarchy, n-1, n-2, and so on, but it does not. It only depends on the two-point function. So it means if you know the two-point function, then this kernel is the same for any n point. And this is the reason why you have the same coefficients in all of these functions. And then you see under this form, the equation is linear. So at the fixed point, with some algebra, you can solve it at the fixed point. And this is a result you obtain that I've shown you earlier. And in fact, these coefficients alpha here are just related to this kernel here. And they are the same for any n-point function. OK? So I'm done with the derivation. So now you can wake up, those who fell asleep. And I'm going to talk briefly about the second part, about the stochastic Kardar-Paris-Lang equation. So what I'm looking at is Berger's equation, OK? Forced Berger equation. And a special case of it where, OK, if you define a velocity, which is a gradient of a scalar function, which we call height, and you enforce that the velocity is irrotational, then in fact this equation maps exactly to another equation which was proposed in a completely different context, which was derived by Kardar-Paris-Lang in 1986. And this equation, what it's described, is an interface that grows under some stochastic process and that becomes rough as it grows. Okay? And I will consider this case of Berger when it maps to KPZ. But what it means that if you look at the forcing, in fact, it has a Q square. So it's not the case where you have a large-scale forcing, because what I put here in Berger's is rather a thermal noise. Okay? So in this game, in fact, in 1D, it will reach an equilibrium, so you don't have shock in there. So it's a different situation than the one you are used to, probably. Okay. And so I will describe the physics of that in the language of the interface. And what you observe, in fact, is that the interface always becomes rough as they grow. Rough meaning they develop very large fluctuation, height fluctuation, and they do so in a scale invariant manner. So if you look, for instance, at the correlation function, it grows in time, in a space, with an exponent chi, which is called roughness exponent. The fluctuation also grows in time with an exponent beta, which is called growth exponent. And as usual, when you have power laws, in fact, if you look at the function of two variables, everything collapses into a universal scaling form. And the scaling variable is this ratio t over x to the z. So z is called the dynamical critical exponent, and it gives you the scaling between space and time. Okay? So if you forget about the nonlinearity, so you obtain just a diffusion, stochastic diffusion equation, and this was proposed by Edwards and Wilkinson. And in this case, well, nothing happens. So you have an equilibrium growth, so you have a time reversal symmetry in all dimensions, and you obtain that z equal 2. So this is just diffusion. Z equal 2, it means you have diffusion, and the roughness is equal to that in all dimensions, so it's 1/2 in d equal 1, so it means that it's a Brownian in space. And in higher dimension, in fact, it remains smooth. But with the nonlinear growth, so first you have an identity which comes from Galilean invariance in all D, which fixes a relation between chi and z. So in fact, you have just one independent exponent. And it turns out that you have an accidental time reversal symmetry in the nonlinear case, but in 1D only. And so it fixes this exponent to 1/2. So it's also a Brownian in space in the stationary limit. But you see that the dynamical exponent is really different. You have 3/2 instead of 2, so it's a huge correction. And this is a super diffusive dynamics. Okay? And in other dimensions, the exponents are not known exactly in KPZ. Okay. And just to tell you that, in fact, this is an extremely large universality class. So it has been studied in many beautiful experiments, including liquid crystal or cancer cells. And at the moment, in fact, it has become in the last 5 years a hot topic in quantum systems, because in fact, KPZ has been shown to emerge very surprisingly, for instance, in integrable Heisenberg spin chain, in driven dissipative boson-chain condensate, in Anderson localization, and many of this has been verified experimentally. So it's really a kind of a big activity at the moment in quantum system. Okay, this was just a comment. So let me tell you what is known in any dimension about this. So I will write it as a path integral. So this is the action. And you can rescale everything so that you have only one independent coefficient, which is a kind of effective nonlinearity. Or you can call it Reynolds equivalently. If you are in Burgers, just call it Reynolds. And in fact, what is known, so renormalization group was used to study this. At Waterloo border, it was done in the original KPC paper. But in fact, it was also found 10 years earlier in the seminal paper by Forsten, Nelson, Stephen, where in fact it's their model A. They did find this D equals 3/2 scaling in 1D. So it's interesting. And it's this point here. So this point is this graph is a scheme of the phase diagram as a function of the dimension of the effective nonlinearity. So below 2, the interface always becomes rough. But from D equal 2 and above, you have what is called a roughening transition. So depending on your initial nonlinearity, if it's too weak, your interface will remain smooth. So described by the Edward Wilkinson diffusive equation. And above this, you will go in the KPZ rough phase. So if you want to describe that, and you have a natural epsilon this time, which is the distance to this lower critical dimension. And in fact, the two-loop calculation was done in the mid-90s by 3 groups in parallel, and they all came up with 3 different results. So just to tell you that the calculation is a bit involved, one of them was correct, though. And in fact, a few years later, it has been shown that if you go to the Kohlhoff framework, in fact, it can be resummed to all order in perturbation theory. So it's a case where you know your whole theory has all order in epsilon. And so with this, you can describe perfectly the roughening transition fixed point. So you find the exponent. But on this side, you just find that your flow runs to infinity. So it cannot find KPZ fixed point. It fails to find it at any order in perturbation theory. So this is really a non-perturbative fixed point. Okay. Maybe I should accelerate a bit. So in 1D, in fact, the equation is essentially solved. There have been many beautiful mathematical results about, so distribution is known. You have universality subclasses with really non-Gaussian distribution, Tracy-Whedon that come from random matrix theory. The 2-point correlation functions are known. They are related to array processes. So it's really beautiful work of the last decade or 15 years. Yet, it still holds a surprise, even in 1D, and this is what I want to talk about. And the surprise came from 3 different papers in around 22, where they look either in the KPZ burgers or in a quantum system that belong to KPZ. They look at the inviscid limit, so infinite Reynolds, if you want. And what they found is beside the superdiffusive exponent that you expect, the Edward Wilkinson one, there is another one, which is Z equal 1, and which is just completely absent from the exact solution. So it was not explained. And the question is, okay, but where does it come from, this exponent? So let me describe just in 2 minutes what they did in this paper. So they simulated burgers, so Galerkin truncated burgers, preserving all the symmetries, so you're really in the KPZ case. So equilibrium in space, so Brownian motion in space, so this exponent is always 1/2 because you satisfy the fluctuation dissipation theorem. But they found 3 regimes in time. And the way to quantify this is by measuring the decorrelation time, defined at the time at which your correlation has fallen off to half its value. And this is a manner to read off the dynamical exponent. And what they observe is the following. So it's compensated by the KPZ scaling. So here, you see that at small k, you always end up with a flat line. So this is kpz. And this means this exponent here. At large k, in fact, at large k, it means small distance, your nonlinearity is not effective. So you expect, in fact, to find a diffusive behavior, and this is normal. This is expected. This is what you observe here. But the surprise comes from, if you take nu to 0, you see that another scaling emerges, which is z equal 1. Okay? So this behavior concerns large k. So it means that it's not an IR fixed point. It's really UV. Okay? This is something that controls the large k. And in fact, you have only one copying constant, so nu to 0 means g to infinity. And it's interesting that the non-perturbative side also rises, in fact, in 1D. And a possible scenario is that, OK, you have kpz fixed point here, and the trajectory, the renormalization trajectory, connects it to Edward Wilkinson. But then if you come from the other side, so from large G, there must be another trajectory that connects it to another fixed point, which we call inviscid Burgers, because it's an inviscid limit. And so to study that, you really need to be non-perturbative. So first, within the very simplest approximation, so just looking at the running of this coupling, in fact, you do find the kpz fixed point. So you're already beyond the perturbation theory tool order. And if you refine a bit your approximation, well, in 1D, you can compare with exact result. And this is a result for the scaling function, so the correlation function. And it's compared to result to prior Ferencz-Spohn, and you see that you have a really, really precise agreement. In particular, if you look deep in the tails here, it was shown in the exact result that you have a stretch exponential with superimposed tiny oscillations. But look at the magnitude here. Those are really tiny, tiny features, but we can capture them with functional RG. And you can compute in other dimension because, OK, you have the fixed point in all D. So let me come back to this nu to 0 limit. So as you would do in dynamical system, if you have a fixed point at infinity, you can change variable so that your infinity is mapped to 1. OK? And if you look at, you can compute the flow equation of this variable, and it has this form. So eta is an anomalous dimension. It will give the chi, and it's defined like this. OK. But clearly, if you look at fixed points, so meaning this term 0, there are 3 solutions. Either this term vanish, and then this is just Edward Wilkinson, and it's UV stable. Either this term vanish for omega W being non-zero or non-1, and then, in fact, this is a kpz fixed point, and the exponent is fixed exactly by the symmetries. So you recover the super diffusive behavior. But you clearly have another solution, which is W equal 1, and this is the inviscid Burger fixed point. And in fact, you can evidence it if you integrate this flow equation. From any initial condition, you will reach kpz. But if you want to look at UV fixed point, you can just run the flow backwards, because then you reverse the stability of your fixed point. And from below, you always end up in Edward Wilkinson, so this is here. But if you start from above, on the other side, you saw that you indeed reach another fixed point, and this shows the existence of this other fixed point in D equal 1. And in fact, we have extended this calculation to all D. So this is a complete phase diagram of kpz, with kpz fixed point, roughening transition, and in fact, this EB fixed point exists in all dimensions. And we found, and I can explain in 2 minutes, that in fact, Z is equal 1 in any dimension, so it's super universal, which is not the case for kpz. The exponent at the kpz fixed point do depend on the dimension. OK. And OK, very rapidly, in fact, we can demonstrate this Z equal 1 in a very similar fashion. Because in this case, if you look at the symmetries of this equation, you have time gauge invariance, and it turns out that you also have a shift symmetry, which come from irrotationality. So these are details I won't explain more. And in fact, you can redo the exact same calculation, and you can close exactly the equation. And not surprisingly, you obtain a similar result. So at small time, again, this proves that Z equal 1. And this calculation, in fact, is valid in any dimension. It gives you the form of the analytical, of the scaling function. Okay, it's maybe a bit deceptive. It's just a Gaussian, but it matches the result from the simulation. So here's a point at the numerics from the previous paper I've shown earlier. But interestingly, you see that there is again this crossover at large time, which is predicted here. And if you look at the numerical data, you see that they don't collapse anymore here at large time. And this is plotted as a function of PT. And in fact, it should not collapse if you believe this regime. So this seems to be an indication that you indeed have a crossover. But the numerics were not precise enough to really conclude on an exponential. OK, so conclusion, this Z=1 scaling at large P, in fact, is very generic, because it's just a consequence of the symmetries. As soon as you have Galilean symmetries and some shift symmetry, you will generically find this. So this leads me to my conclusion. And in fact, I've shown you that it emerges in Navier-Stokes, in passive scalar by Kraichnan, and also in Burger's KPZ. OK, so all that concerns time dependence. So as a perspective, it would be very nice to go back to equal time properties, structure function. And OK, it would be nice in particular. We have an estimate of KPZ exponent in only, but that's not very good at high D. So we would like to improve that by using the existence of the implicit Burger's fixed point. And we have started, in fact, to compute that in simplified models of turbulence, which are shell models. And here we could show that, indeed, you have anomalous exponent for S2. And OK, the ultimate, so the dream of Laurent, maybe. So my dream would be to have an estimate of anomalous exponent in Navier-Stokes. And with this, I thank you for your attention. This is Grenoble, under the clouds, so my lab is somewhere here.